autonomous driving still struggles with motion blur and high dynamic range lighting. Standard RGB cameras and LiDAR miss critical details when exiting tunnels or tracking fast-moving objects. Enter dynamic vision sensors or event cameras. Unlike frame-based sensors, DVS pixels trigger asynchronously only when brightness changes exceed a set threshold. That gives you microsecond temporal resolution, over 120 decibels of dynamic range, and zero motion blur. Researchers at AGH University built InterFuserDVS to fuse this data into an end-to-end driving pipeline. They process multi-view RGB, LiDAR projected into a bird's-eye view, and DVS event frames. Each modality runs through a ResNet backbone, then gets flattened into fixed-dimension tokens. Crucially, they initialize the DVS encoder with pre-trained RGB weights to leverage the spatial correlation between static intensity edges and temporal brightness changes. All tokens concatenate and pass through a 6-layer transformer encoder with 8 attention heads. The global attention mechanism dynamically weights sensor importance based on environmental context. But raw predictions aren't enough for safety. The decoder outputs waypoints, traffic light states, and object density maps. A hybrid safety controller then renders these into a local occupancy grid, checks predicted collisions at multiple future time steps, and mathematically overrides the PID controller if the safe distance drops below a velocity-dependent threshold. On the CARLA leaderboard, this architecture achieves a 77.2 driving score with perfect route completion, drastically reducing pedestrian collisions by catching high temporal contrast motion that standard cameras miss. The next step: moving past frame accumulation entirely. Future work proposes spiking neural networks paired with an asynchronous fusion transformer to process raw event spikes in real time, unlocking true microsecond reaction times for safety-critical maneuvers. The full paper and code are linked below.